Physics is about the relationship among different physical quantities. Some relationship remains unchanged when a physical system undergoes transformation. The invariant of a system, often expressed in equations, is the law governing the system. Any law, if true and fundamental, shall be observed by all equally. Otherwise, the law cannot be considered truly fundamental. The current laws of physics, however, often give preferential treatment to different particles. For example, light enjoys a privileged status in modern physics. The speed of light in vacuum is constant in all directions, independent of the motion of the light source. The important equations in modern physics revolve around light or its speed c. The lowly objects living on the planet Earth might wonder, what's special about light or vacuum? Why do they get special treatment in the eyes of physical laws? The fundamental laws of physics, quantum mechanics and general relativity, rule the world of extremely small and extremely large with an iron fist. This time, the particles in the middle seem to have great leeway how to observe the same laws. Free-spirited physicists happen to live at the center of this comfortable zone. They theorize that elementary particles are the superposition of discrete quantum states. Yet, no theoretical physicists ever confess that they're half-dead half-alive zombies. They theorize that various quantum fields exist everywhere in space, and the excitation of the fields gives birth to elementary particles. Yet, no theoretical physicists just sit there and wait for the excitation of love field to create baby physicist for them. No one really takes their omnipresent quantum fields seriously in their everyday life. According to Newton, an object travels in a straight line at a constant speed unless a force acts on it. But, physicists themselves wander around on the Earth freely. No one explains what forces cause their arbitrary motion except their free will. According to Einstein, the largest objects curve spacetime for the smallest objects in the universe. But, physicists themselves don't seem to be bothered by the curvature of spacetime. No one tries to apply these equations to their everyday life. No one explains why random particle interaction inside their brain gives them the desire and ability to contemplate the laws governing the universe. No one explains how the laws of physics led to the evolution of life, the universe, and everything. In a sense, physicists today are as privileged as the priests who tried Galileo 400 years ago. They're still situated at the center of the universe, and the laws of physics revolve around them. They cannot help but formulate the laws of physics from humans' point of view. Physical quantities are measured relative to reference objects used as the units of measurement. In order to formulate the laws from the perspective of individual particles, we need to use proper ruler and clock, and a system of natural units. When proper units are used, the invariants of a system are obvious. The laws of physics can be expressed in a few simple equations. When wrong units are used, the patterns among different quantities are obscured. The laws of physics become elusive. Traditionally, some random object is chosen to provide the basis for the unit of length. For example, ancient Greeks and Romans lined up a bunch of people, and used the average length of their feet for the unit of length. The French people decided the unit of length should be 1/10,000,000th of the distance between the North Pole and the equator along the meridian through Paris. The SI unit of length is based on the wavelength of light in vacuum because the constant speed of light plays a special role in modern physics. Similarly, ancient people derived their sense of time from the circular motion of celestial objects. They naturally choose the moving cycle of the Earth, the Moon, and the Sun as the basis for the unit of time. Human physicists decided that the SI unit of time should be based on the oscillations of cesium atom because of its high resonant frequency. The hidden assumption for choosing an absolute ruler and clock for all particles is that universal spacetime exists independent of individual particle interaction, and that different particles share the same spacetime. This is probably the most flawed assumption in physics. From the perspective of a walking Kinesin, the units of length and time chosen by human are arbitrary and irrelevant. Its motion is not affected by the wavelength of a photon or the oscillations of a cesium atom. Its universe evolves because of its interaction with microtubules and ATPs in the environment. It is individual particle interaction that creates points with relative position and direction, and moments that separate the past from the future for a walking Kinesin. Without particle interaction, nothing changes in the world of walking kinesins. If nothing changes, space and time have no meaning. When a kinesin binds to a microtubule, it's a walking kinesin. When a kinesin's detached from a microtubule, it becomes a free kinesin. A walking kinesin and a free kinesin are two different species. They live in different spaces and behave differently. A free kinesin exists in a three-dimensional space defined by its thermal environment, and undergoes random Brownian motion. A walking kinesin exists in a one-dimensional space defined by a microtubule, and produces distinct walking motion. For a walking kinesin, its space contains only a set of discrete points, which are kinesin binding sites on a microtubule. A walking kinesin can never reach any point beyond these binding sites. The boundless three-dimensional space conceived by human brain makes no sense for a walking kinesin. The curvature of a microtubule, on which a kinesin walks, determines the geometry of its space and guides its movement. The size of tubulant subunits determines its step size. The tubulant subunits may expand or contract as temperature changes. A kinesin walks on them experiences the same thermal expansion or contraction. Its step size has nothing to do with the length of a man's foot, the diameter of the Earth, or the wavelength of light. Similarly, time is not absolute either. Each particle interacting system has its own clock that ticks at its own rate. There is no universal time shared by all particles. In a quantum system, time is a set of discrete moments. Time jumps from one moment to another. The flow of time is tied to the consumption of energy, which is a function of its thermal environment. For example, when temperature drops in the winter, Alaskan wood frogs get frozen. Their metabolism and energy consumption grind to a halt. This pauses the flow of time for all biological interaction inside the frogs. All walking kinesins stop moving. When temperature rises in the spring, these frogs come back to life. This resumes the flow of time for biological interaction. Kinesins start walking again. The freezing of the time is a dramatic event to outside observers, but it's a non-event for the walking kinesins inside a frozen frog. They just walk as usual from one tick of their private clock to another. How many Earth days or cesium seconds have passed between two of their clock ticks is completely irrelevant to them. We can manipulate the passing of time experienced by walking kinesins in a lab. When a thin slice of cell sample is dropped onto a metal block cooled in liquid nitrogen, this quickly freezes the flow of time for kinesins in the sample. If the thermal environment, mostly water molecules, is removed by evaporation, we can get a high-resolution image of the frozen world using electron microscope. If water molecules are not removed, we can restore the environment by raising temperature. This effectively resumes the flow of time. Kinesins will walk as usual, as if nothing happened. Let lambda I denote the size of step I, and n denote the total number of steps observed in an environment. The mean value of all step sizes, lambda, should be very stable in an environment at thermal equilibrium. The value of lambda may change over the time as the macroscopic environment evolves. But, in a microscopic region like a living cell, lambda remains constant for a given period of time. Let's define the mean value lambda as the unit of length for walking kinesins. Similarly, let tau I denote the time period of step I, and n denote the total number of observations. We can define the mean value of all time periods tau as the unit of time for walking kinesins. The value of tau remains constant in an environment at thermal equilibrium. The unit of length lambda is the average dimension of one walking cycle. The unit of time tau is the average duration of the same walking cycle. They are natural units derived from the fundamental unit action h. The unit of length and the unit of time are tied to the same particle interaction. It's the root cause why space and time cannot absolute. They're two physical quantities describing different aspects of one particle interaction. Space and time are a set of discrete points that emerge from the same action h. It's the origin of Einstein's inseparable spacetime. Let delta x be the distance traveled by a walking kinesin. Delta x equals the number of steps n times the unit of length lambda. Let delta t be the time interval. Delta t equals the number of steps n times the unit of time tau. The speed of Kinesin walking along a microtubule, c, equals delta x divided by delta t. Substitute x with n lambda, and t with n tau. Cancel out both n. The speed c equals the unit of length lambda over the unit of time tau. Since both lambda and tau are constant, speed c must be constant too. In a thermal environment, microtubules could point to any random direction. The equation predicts that the speed of walking kinesins is constant in all directions. The prediction can be tested via experiments. This video captures microtubules gliding over Kinesin-coated surface. Most microtubules shown here are about 5 to 10 micrometers long. A Kinesin step is about 8 nanometers in size. A microtubule to a Kinesin is like a couple of thousand feet pole to a man. Kinesins are not directly observable here. The moving microtubules show the relative motion of walking kinesins. They travel in all directions, and their speeds are pretty constant. Note that the system operates in a chaotic thermal environment. A constant speed here means that the probability distribution of observed speed is very narrow compared with the Maxwell-Boltzmann distribution of the speed of the same particle in the same environment. Some microtubules occasionally fall off Kinesin-coated surface. You can get a sense of their typical motion in the same environment. If your last name were Einstein, this should be your Michelson-Morley experiment. Einstein developed his theory of special relativity based on the constant speed of light. Here, the constant speed of walking kinesins is a derived result from the first principle of quantum mechanics. The natural units derived from the unit action h are the only relevant units from the perspective of individuals that participate in that action. When the natural units are used, the motion of all step motors looks identical. They all travel in a straight line one step at a time. The result can be generalized for all particles that operate quantum mechanically. That is, a particle travels in a straight line at constant speed, when the speed of that particle are measured in the natural units of length and time derived from the unit action h. In three-dimensional space, the distance delta d between 2 points is defined using the Pythagorean theorem. The square of delta d equals the sum of the square of delta x, delta y, and delta z. Two observers may measure the x, y, and z position of the 2 points using different coordinate systems. The distance will be the same for both observers, as long as they're using the same units. We say the distance is invariant under different coordinate systems. It's the basis for two observers to agree that they live in the same physical reality. Because speed c is constant, we can think c as the conversion factor between distance delta x and time interval delta t. Delta x and c delta t have the same units. We can similarly define the distance delta s between two events in spacetime using the Pythagorean theorem. The square of delta s equals the square of delta x minus the square of c delta t. We're using minus instead of plus here because space and time are different, and we cannot just treat time as another dimension of space. We will explain what's the essential difference between space and time in the future. For now, let's accept the definition as it is. Substitute delta x and delta t with n lambda and n tau. Replace speed c with lambda over tau. Cancel out tau. The spacetime interval delta s equals 0. The spacetime interval remains unchanged for all who observe constant speed c. The constant spacetime interval is also known as the Lorentz invariant. It is the basis for two observers to agree that some event takes place in their shared reality. The core postulate of Einstein's special relativity is that the laws of physics are invariant under the Lorentz transformation. To re-examine what Einstein got right, and how he might be wrong, we need to resolve a few more fundamental issues in our understanding of quantum mechanics. The true invariant that underlies this identity can be expressed in a different form. The distance x measured in the units of lambda equals the number of steps n. N is also equal to the time interval t measured in the units of tau. Let's get rid of n. Move all physical quantities to the left side. What's expressed here is spacetime invariant for all physical systems. Note that the sign of time t is the opposite of the sign of position x. It means that any physical quantity derived from the unit time tau always has a counterpart associated with the unit length lambda. The total amount of two physical quantities is always conserved. Ever since Galileo dropped two bodies of different masses from the Leaning Tower of Pisa, physicists keep making rules to govern the motion of different physical systems. As they study more systems, they discover that some physical quantities are always conserved. They realize that conservation laws are more fundamental than individual rules. In 1915, mathematician Emmy Noether proved that a conservation law is always associated with a differentiable symmetry of the corresponding physical system. It's a powerful insight into any general theory in physics. Einstein complimented her as one of the most significant mathematical geniuses. But, neither Einstein nor Noether questioned why symmetries exist in the first place. Both took spacetime and symmetries associated with it for granted. All symmetries in spacetime are originated from this identity. It is the mother of all conservation laws. Euler's identity is often considered the most beautiful equation in math. On one side of the equation is the number 0. It could mean nothing or everything in physics. On the other side of the equation, four mathematical units are linked by three basic arithmetic operations: addition, multiplication, and exponentiation. The number 1 is the natural unit of counting number. The number e is the natural unit of growth and evolution. The number I is the square root of -1, the imaginary unit of complex number. The number pi is associated with a circle. A circle represents a cycle of repeated operations. But, there is an imperfection in the commonly cited form. Pi is only a half cycle. The natural unit of a cycle should be 2 pi radians. Euler's identity can be rewritten in a different form. Let's make a copy of both sides. We have two exponentiations on the left, each representing a half cycle. Combine two exponentiations by adding their exponents. Multiply 2 -1 on the right. On the left, the exponent now includes 2 pi radians, the natural unit of a full cycle. On the right, it's a whole number again. The identity unites all four fundamental units in mathematics in the simplest possible way. It's a pure mathematical beauty. However, beauty is only in the eye of the beholder. Neither a photon nor a kinesin can appreciate the beauty in its current form. To marry the mathematical beauty with physical reality, we need to put 0 back to the identity. The 0 is the spacetime invariant we just derived, position x measured in the natural units of length lambda, minus time interval t measured in the natural units of time tau. The identity now contains two variables, position x and time t. They represent any possible combination of position and time that could be experienced by a particle. The order of time component and space component in the spacetime invariant can be switched as long as they have opposite signs. The two opposite configurations are expressed by adding a plus-minus sign in the front of the exponent. Let's do a quick sanity check and make sure the identity does hold. The spacetime invariant equals 0. 0 times anything is 0. The exponent, I2 pi times the invariant is still 0. Anything raised to the power of 0 is 1. Therefore, the identity must hold for any combination of position x and time t. No matter how a particle moves in spacetime, its position x at time t must satisfy this equation. In other words, the identity prescribes the rule that governs the motion of all particles. If Euler's identity is the most beautiful equation that's only appreciated by human brain, this identity is the most beautiful equation that must be observed by all particles in the universe. It's the basis for all particles in the universe to agree that they are governed by the same laws of physics. We will call it the universal identity. Let k be the conversion factor between the unit circle 2 pi radians and the unit length lambda. Let omega be the conversion factor between the unit circle 2 pi radians and the unit time tau. K is known as wave number, and omega is angular frequency. Substitute 2 pi over lambda with k, and 2 pi over tau with omega. The universal identity is expressed in the simplified form, e to the power of plus minus I, times kx minus omega t, equals 1. This simple identity will help us to derive the laws of both classical and quantum physics. Previously, we discussed that the state of a quantum system is represented by a complex number. The state of a composite system is represented by the sum of all subsystems. Quantum system here means any physical system that executes one action at a time. It includes all molecular machines like walking kinesins. It also includes but not limited to all elementary particles like photon. In our formulation of quantum mechanics, the evolution of a quantum system is represented by multiplying its state by a pair of complex conjugates. The plus-minus signs signify two opposite systems. One system produces positive actions, corresponding to steps walked by red kinesins. And the opposite system produces negative actions, corresponding to steps walked by green kinesins. Two opposite actions cancel out each other, and the center of the combined system doesn't move. The multiplication rotates all complex numbers by 2 pi radians, a full circle. This models an evolution step advanced by the underlying physical systems. The area swept by rotating arrows is proportional to the amount of actions executed by the corresponding systems. Our formulation of quantum mechanics is backward compatible with the version developed by the generation of Schrödinger, Dirac, and Feynman, but there are some key differences between two formulations. If you haven't watched the video yet, please check the link below. Let phi 0 be the initial state of a quantum system. Multiply phi 0 by 1. The result of multiplying a number by 1 is still that number. In physics, it means that the operation doesn't change the state of the underlying system. Substitute 1 with the universal identity. This operation shouldn't change the nature of the underlying system either. But, it creates a complex function phi with two variables, position x and time t. Given any input x and t, the function outputs a complex number. The number represents the state of the system at position x and time t. Therefore, function phi of x and t dictates how a quantum system evolves in spacetime. How do we know that the function prescribes the right laws? A simple test is to see if it satisfies the Schrödinger equation. The Schrödinger equation is a linear partial differential equation that governs the wave function of a quantum system. The left side of the equation is the first partial derivative with respect to time t. Replace phi of x and t with the actual function. The derivative of exponential function of base e is the function itself. Apply the chain rule. The derivative of the exponent ikx minus omega t with respect to variable t is the coefficient of t. It equals minus I omega. Flip the plus-minus sign to minus plus. The first term is the original function phi of x and t. Combine all constants. By definition, the square of the imaginary unit I is minus 1. This flips the sign back to plus-minus. According to Einstein, the fundamental unit action h bar times angular frequency omega equals energy. The plus-minus sign represents two opposite systems that produce a pair of action and counteraction. Dirac calls them particle and antiparticle. Newton calls them action and reaction, which are essentially the aggregated effect of a large number of microscopic actions and counteractions. Let E sub plus and minus denote the stationary energy stored in a particle. The left side of the equation equals E times function phi of x and t. The right side of the Schrödinger equation includes the second partial derivative with respect to position x. Similarly, the first derivative of phi with respect to x is, to move the coefficient x in the exponent, plus minus ik, to the front of function phi of x and t. The second derivative of phi with respect to x has two sets of the coefficient. The square of plus or minus equals plus. The square of I equals minus 1. These two squares result in 1 minus. Two minuses cancel each other out. Combine all constants. The action h times wave number k equals momentum. The square of momentum over 2m defines kinetic energy. The equation has three terms. Each contains phi of x and t multiplied by one form of energy. Where E sub plus minus is stationary energy, Ke is kinetic energy, and V is potential energy. Move all three terms to one side of the equation. Group the common term phi of x and t. The term in square brackets represents the conservation of energy, namely, stationary energy E minus kinetic energy Ke and potential energy V always equals 0. Therefore, function phi of x and t represents a valid solution to the Schrödinger equation, and the solution also implies the conservation of energy. We just deduce the wave function without any heavy machinery of modern physics. The only assumption we make about a quantum system is that it executes one action at a time. We argue that physical quantities must be measured using the natural units derived from the action that defines the system. From the natural units of length and time, we deduce constant speed c. The constant speed c is a manifestation of the space-time invariant. The space-time invariant is an inherent property of a quantum system. Marrying the space-time invariant with Euler's identity, we deduce the universal identity. From the universal identity, we deduce the wave function that governs the evolution of a quantum system. The derivation depends only on the space-time invariant, and nothing else in physics. The derivation uses only the basic arithmetic of complex numbers, and no calculus or advanced math involved. For some people, the derivation must be true because of its simplicity and beauty. For others, the derivation seems too simple to be true. They spend their lifetime studying the wave function. Yet, they dare not say that they fully understand quantum mechanics. How could the law governing the motion of all particles be deduced so easily? Imagine that you're a photon or a Kinesin, and none of your kids could possibly understand calculus, not to mention the Schrödinger equation. How do you explain the law of quantum mechanics that they must follow in their everyday life? The solution is surprisingly simple. You just tell them to continuously explore their immediate environment one step at a time. It's a simple rule that all particles can understand and execute faithfully. It's the rule expressed in this equation. If physics is ever taught in the universe by anything other than human, it might not take a detour of the Schrödinger equation, but it has to be a version derived from this equation. The universe is discrete and everything has to be quantized. That's the essence of quantum mechanics. It's ironic that the law governing discrete world was first expressed in a partial differential equation. The wave function, as formulated by Schrödinger, requires space and time to be continuous and differentiable. Its interpretation has puzzled many geniuses, including Feynman and Einstein. Heisenberg has to make a rule called the uncertainty principle to prevent such a formulation from collapsing. The wave function, as deduced by us, doesn't require anything to be continuous and differentiable. The derivation can be understood and retold by most kindergartners, if, at an early age, they're taught and think in the symbolic language of complex numbers. Complex number phi is a noun. It represents the state of a physical system. In a natural language, we use a string of characters to represent a physical object. In a computer, all characters are encoded as numbers. So, nothing really new here. A subscript or a superscript is like an adjective. It modifies or describes the noun. For example, phi sub 0 means the initial state of the system. An equation is a statement. The summation states that the system of phi is made of any number of subsystems. Each subsystem is represented by a complex number, phi super k. The equation states that the initial state of the combined system, phi sub 0, is the sum of the initial state of all its subsystems, phi k sub 0. Multiply is a verb. It means evolve or advance in English. E to the power of I2 pi is a unit circle on complex plane. It's a noun representing an evolution step. The plus-minus sign means two opposite evolution directions. The number 1 means one step. This expression reads, the system evolves one step forward from the initial state phi 0, and the new state of the system is phi 1. The system continues evolving, one step at a time. After n steps, the state of the system is phi n. The equation states how a physical system evolves as a function of step n. The step n can be expressed as position x in the units of lambda, or as time t in the units of tau. Divide the equation with e to the power of I2 pi t over tau. This creates a wave function that governs the motion of a quantum system. The wave function is specified by two base units, lambda and tau. They are the natural unit of length and time derived from the unit action h. The function describes how the evolution of a quantum system unfolds in spacetime. Many classical and biological systems execute one action at a time. If we can identify the unit length lambda, and the unit time tau for a physical system, we can have a set of rules governing the motion of the system. For step motors like Kinesins, lambda is the average step size, and tau is the time interval of one walking cycle. For elementary particles, lambda is the distance of one wavelength, and tau is the time interval of one period. If there is no problem in our derivation, their motion should be governed by the same wave function. But elementary particles and step motors look so different. Step motors always travel along some kind of guide rail. Elementary particles seem to travel in three-dimensional space freely, and their motion are not constrained by any kind of guide rail. How could possibly their motion follow the same wave function? More importantly, why does a particle have a wavelength? Where in the world does the wave come from? The questions remain unanswered for over a century. We have to resolve the issue in order to have a better understanding of how the universe operates. If you find the content in this channel is interesting, please click the like button below, subscribe, and share it with your friends. It will help to connect those who are also interested in the topic. Thank you very much for your help.